Okay, I guess I will just get started with the ground rules. So we will take questions at the end. If I think the easiest way to do that is via the Q&A panel here. But you may also be able to raise hand, and if so, I will be keeping track of raise hand and we can have people ask questions that way. But I think the preferred way is by typing it into the Q&A, and then we'll read the question. But we're now over 30 people, and given the fact that we have an SPIE that has had quite a bit of our colleagues in it, I think that's a pretty good number. So we will start. I'm Randall Smith, and I'm very pleased to be introducing Manami Sasaki. For those of you who don't know her, she got her PhD at MPE under Professor Joachim Trumper, sorry. She then came to CFA as a postdoc, which is, I believe, where we first met. And then after a short break, went back to Germany and to Tübingen as a postdoc, and then a group leader, and then a Heisenberg fellow, which I gather means that you can't tell if she's a fellow or not unless you're looking directly at her. She has since gone on and is now a professor at Erlangen, FAU, and she is a member of many consortiums and instrument teams, including Athena, eRosita, Lightbird, HESS. Her general field of study is stellar endpoints, including white dwarfs, neutron stars, black holes, X-ray binaries in our galaxy and others, supernova remnants, which is, I think, where we first interacted a lot, since we both work on supernova remnants, and the interstellar medium in ours and nearby galaxies, including the Magellanic Clouds. So today she'll be speaking on Beauty of the Beast, supernova remnants seen in X-rays. Please take it away.
Thank you, Randall. Yes, hello everyone. I'm Manami Sasaki, and it's my pleasure to be here and to give this talk. Yeah, I've been working in X-rays for quite a long time, as you have seen, since my PhD studies. And I think supernova remnants, as I said, as Randall also said, is one of the main topics that I've been working on, and I'm still working. And I think it's also one of the reasons which made me stay in X-rays. And you might understand why if I finish talking about all the interesting things that you can do studying supernova remnants. And you also heard a lot of German names. It might be confusing, but the reason is I am located in Bamberg, where you see the picture of the observatory. Some of you have been already there. It's a very nice old observatory. That's a city close to Erlangen, where our university is located. But this university, Erlangen, is also located to Nuremberg, close to Nuremberg, which is one of the major cities in Germany. And the university is called Erlangen-Nuremberg. So that's why you hear all these names. But they're located in the beautiful Bavaria, in Germany. So, and yeah, especially Bamberg is a very nice city. So if you're nearby, you should definitely come by. But yes, let me now start talking about science. So supernova remnants, as you most likely know, is what you get if there is a supernova explosion. I'm not going to go into the detail of the different types of supernovae, but you will see that this has also some implications for what we see. So in general, what makes a supernova is the fact that there is a strong shock wave that is created by this explosion. And typically strong shock waves, if they run through a medium, especially in the interstellar medium, what happens is that the gas in which the shock wave is located is ionized and is heated to very high temperatures. So supernova remnants are typically the heating source in the interstellar medium in a galaxy. And also supernova remnants, since it will distribute all the matter that was processed inside stars, it also acts as sources of heavy elements in the galaxy. And what is also very important is the fact that in such strong shock waves, particles can be accelerated to relativistic energies. Therefore, supernova remnants are also one of the important sources of galactic cosmic rays. And in general, if you have such strong shock waves, it will create new structures in the interstellar medium, also have an effect on the star formation. So it's very important for the evolution of galaxies. What you see here as images are the remnants of the historical supernovae, all seen in X-ray, in all in their glory. Tycho's supernova remnant, Kepler's supernova remnant, and the supernova remnant Cassiopeia A. And these are all Chandra images. And so even though I said supernova remnants are well seen in X-rays, they can be actually observed over the entire electromagnetic spectrum. And typically they're very bright in radio, in which in a band where you can see a strong emission coming from electrons that are accelerated in the shocks and emit synchrotron emission. That's what you see in the case of Cas A on the very left, in the very left image. But then you can also study other parts of the supernova remnant, like the ejected material, the stellar material. That's what you can, for example, see in this infrared image, where you have the still cold material that has been ejected from the star and is now gradually being heated. And in a supernova explosion, that can also be processed, so created or also destroyed or changed. And that's also why it can be a supernova remnant can be bright in infrared. In such shock waves, material also ionized plasma material can become dense, can be swept up, can become dense, and then also emit radiation line transition through atomic transitions, ionic transitions. And these transitions you can see in the optical, and that's what you see in this image, in also for Cassiopeia A, where you see this this region around the ejected material, bright, showing bright filaments in the optical. And then, as we said before, in X-rays you have the hot plasma that has been heated by the shock waves, and that's mostly emitting thermal emission, but in some cases we also observe non-thermal, so X-ray emission from non-thermal particles. And then if you go to even higher energy gamma rays, so from MeV up to TeV, you will also see different things like emission coming from the radioactive decay, non-thermal Bremsstrahlung, or inverse Compton, or even pi-0 decay from particles interacting with the surrounding, so accelerated particles interacting with the surrounding. So supernova remnants are among the interesting astronomical objects that can be observed over the entire range of the electromagnetic spectrum. And you can use all these pieces of the puzzle to put it together and understand the entire physics and the evolution of such objects. But as I said already before, the main driver why you get such an object is the interstellar shock that is produced by the supernova explosion. Therefore, I just want to spend 1 or 2 slides on interstellar shocks. So shocks in general are very common in astrophysics. It's not only in supernovae, but also created, for example, by stellar winds, or you will see shocks in accreting objects, or also even at lower energy is in H2 regions, for example. And what you do is you look at the interstellar medium, and you can, even though it's such a thin medium, it can be regarded as a fluid, as a compressive medium. So therefore, if there is some pressure-driven disturbance, like an explosion, it will run a wave which will then be faster, expanding faster than the sound speed in that medium, and this will create a shock wave, which is just a discontinuity in the physical parameters, like density, velocity, pressure, which can be used to describe this medium. And what happens if there is such a shock wave is that the energy, that the kinetic energy that these shock waves have is converted into heat. And that's also the reason why you will end up with such hot plasma. Now, typically, if you look at at shock waves and at compressive medium, what you assume is that that the particles in that medium can collide with each other. That's the reason why you can propagate such a disturbance. But if you think about the interstellar medium, you will realize that the interstellar medium is actually very thin. It has a very low density. So typically the mean free path in the interstellar medium is too high to create such a shock wave. But we do see shock waves, like in this example. This is just a shock wave created by one star, by the stellar wind of a moving star. That's why it has such a nice bow shock shape. And the reason that you can get an interstellar shock is because the interstellar medium also has a ionized phase. So typically, if you have a massive star or also an exploding star, the surrounding is not neutral, but it is mainly photoionized, but maybe also shock ionized from other events before. And then you have plasma, you have charged particles, and you have magnetic fields, of course, and these will lead to interaction between the particles that are in the fluid, and then the shock waves can be created. So typically, if you have an interstellar shock wave like around stellar winds or supernovae, we call them collisionless because there is no real collision between the particles, but they are interacting. So if you hear about collisionless shocks in supernova remnants, that's the reason. But that's something, this is also what is also important, and you always need to keep in mind, because since you have such low density, it will take a lot of time for the particles to interact. So once you have a heated plasma, until this plasma reaches equilibrium, it will take a long time. So typically, supernova remnants are objects that are not in thermal equilibrium, which we, in the beginning, when we started looking at observing supernova remnant and analyzing the spectra, often assumed, but this was a very crude simplification. Now, very quickly, as I said, supernova remnants are very bright also in radio, and that's the reason. The reason is because in the shock waves you can accelerate particles, and especially electrons will stay relativistic very long time, and they will efficiently emit synchrotron emission. That's why you see strong, bright radio emission from supernova remnants. Typically, supernova remnants you can find in the radio, or in combination then in X-ray. So that's what you see in the case of Kepler, for example. Here you see nicely the shocked structure, the ring-like structure of the Kepler supernova remnant. On the left-hand side, on the right-hand side, you see the corresponding image also taken with Chandra. And this is an RGB image, so 3-color image. And if you look at the distribution of the blue image, which shows you the hardest band, you realize that so in the parts that you can see, you realize that it looks quite similar to what you see in radio, because that's where the accelerated particles are. And since Kepler is quite young, you can also still see synchrotron emission in the X-rays. And all these other things that appear greenish, yellowish, that's emission coming from the hot plasma. And such non-thermal emission in X-rays you cannot observe in many of the supernova remnants. That's only the case if you have young supernova remnants, like in the case of supernova 1006. This was one of the sources that have been detected as a non-thermal X-ray emitter, a supernova remnant. And here you see a combination of a radio and an X-ray plus optical image. And if people have already early realized that the emission in X-rays in the outer rim is very non-thermal. And here you see spectra taken with Chandra. If you look at the very outer rim, like here, then you see that the spectrum is a power law, of course, folded by the response, so it's not aligned. But then if you go a little inside, then you start seeing the thermal emission. So the also structures that we know that these come from light transitions. And another things also, a thing that also became also possible in the last 2 decades with Chandra and also XMM is that you look at these structures. So this is now Tycho supernova remnant. So before, again in a 3-color presentation. So if you look closely, the blue emission is again at the outer rim. That's where the outer shock wave is located, and it's very narrow. So it's a very defined shock front. And then in the interior, you see the emission coming from the hot plasma. That's a mix of shocked ISM and also ejected material. But then if you only look at the the hard emission, like here, it's again taking with Chandra. Now what you just start seeing is that you see additional structures, interior structures, like stripe-like structures that you see here. Also here, fainter structures, fainter stripes in the interior. So here you can see nicely in this, also in this, again, this young supernova remnant, where there are magnetic fields that are amplified and are stronger, not only at the rim of the shock, but also inside. And this can also tell you about movement and the dynamics inside the supernova remnant. So these stripes, we believe, are made because there is some mixing going on between the shock material, and this will make turbulences and cause amplification, local amplification of magnetic fields, which then increases the synchrotron emission. Now, but in this talk, I would also more like to focus on this plasma emission, like the thermal plasma emission. But before doing so, I just wanted to give you a quick review on, quickly review the evolution of such a supernova remnant. So, Tycho supernova remnant, Kepler supernova, those are rather young supernova remnants. So, if there is an explosion in the beginning, this explosion is expanding very fast, very freely, doesn't see anything. The shock wave doesn't really react on the interstellar medium. This is what we call the free expansion phase. It only takes a few decades or maybe 100 years, hundreds of years. And that's where this expansion is driven by the ejected material. But then soon what happens is due to the interaction with the interstellar medium, there will be kind of a slowing down of the expansion, and there will be a new, an additional shock wave that is created inside the supernova remnant, and then will be propagating in the interior. And this is exactly the reason why you then get a hot interior, or the entire interior of a supernova remnant is heated. So that's a shock that we call the reverse shock, because it's going into the supernova remnant, and this is takes this phase, which we call the Sedov or the adiabatic phase, because the evolution of the remnant can be explained in an adiabatic way. This is the longest time in which we can observe the supernova remnants in X-rays. And here below you see some simulations that have been done by Gilles Ferrand and others. For such an evolution, you see the outer shock, which shocks the, and then behind it, the shocked interstellar medium. And then in green, you have the reverse shock that is now propagating into the supernova remnant. And then you see this mixing of the shock detector and the shock interstellar medium. And what is also important is that in such simulations, one can see that if you include the acceleration of particles, you can reproduce such the emission of supernova remnants very well. And at the end, the supernova remnant will become radiative, which means that a lot of energy is lost through radiation. And that's where we say the supernova remnant is now old and is cooling down, and it at some point will mix with the interstellar medium. Here you see a nice example of such a rather young supernova remnant. It's a brightest supernova remnant in a small Magellanic Cloud, year 1 or 2. It's a combination of X-ray, optical, infrared image, but with this color presentation, you can nicely see where the forward shock is. So the outer rim of this green emission would be the forward shock. And the reverse shock is where this bright emission in the optical and also in the inner end of the X-ray emission is located. And if you now look at the spectrum of such emission, you see something like that. So on the left, you see this CCD spectrum taking of such a thermal plasma from the supernova remnant. In addition, here you see some UV spectrum, and you see a lot of lines from elements that have been produced in the star. For that remnant, we know this is the remnant of a core collapse. So you see a lot of alpha elements that have been produced in a massive star at different stages of ionization, so low ionization to very high ionization, helium and hydrogen-like species of oxygen, neon, magnesium, and so on. And these lines can be used to study the properties of such a hot plasma very well, because you see different transitions, different ionization stages. And for example, here you see a model that reproduces the emission of an X-ray spectrum of such a hot plasma. You have all these continuum, and then you see the different oxygen lines, neon lines, magnesium lines, and you will also have some iron lines coming from not so highly ionized iron. And for example, the line ratio and the amount of the lines, the strength of the lines also depend on not only on the ionization, but also on the history of the plasma. And that's what I mentioned before. You need to take into account in what kind of a state the plasma is. Is it in equilibrium? It's not in equilibrium. This is a calculation that has to be done for a very high temperature plasma, 6 kilo-electron volt. And depending on what you assume as an input, what the composition is, so this is the difference between the upper panel and the lower panel, and also the age of the plasma given by the ionization time scale, which is the electron density times the time scale. Low means that it's still not in equilibrium. High means it's in equilibrium. You see the spectrum will look completely different. So by comparing with such models, we can clearly study the plasma and therefore also the history of such supernova remnants. And like when those CCD spectra became available, that's what we also did. For example, for EO1 or 2, we looked at the position where the X-ray emission was very bright. We looked at the oxygen, helium-like and hydrogen-like oxygen lines, neon lines, and also magnesium lines, and try to constrain the temperature or the ionization timescale by measuring the line ratios. You see the line ratio between the helium-like oxygen triplet and the hydrogen-like oxygen, and the same for magnesium and neon. But just using this, and also with the CCD resolution, it is very difficult to constrain such numbers. So in that case, what we did is also add some UV lines, which will then give you an additional stage of ionization, a lower ionization for oxygen. And by combining these, you see you start being able to confine these the parameters like the temperature and the NET. So this really helps, these emission lines really help to understand the properties of the plasma inside such a supernova remnant. If you look at the spectra, what you also see is depending on, for example, on the type of the progenitor, you will see different X-ray spectra. So here I'm just comparing the EO1 or 2, which we already saw, and we said it's a core collapse spectrum, the CCD spectrum with a grating spectrum. And here below you find a type 1a supernova remnant, also young and very bright in CCD and grating, and you realize the shape of the spectrum is completely different. And that's because here you see all the alpha lines, again, alpha element lines for oxygen, neon. And for type 1a, you see less of those lines, but you see heavier element lines from heavier elements. And especially here, this bump around 1 kV, this is coming from the iron L transition. So by looking at spectra, in high resolution spectra would be the best, but even by looking at CCD spectra, you can also learn about the type and of supernova remnants as well, supernova as well. What you also can do is look at images. This was possible with since we have these imaging instruments with spectral information. So again, Cassiopeia A with this different energy band. So this is the entire band. But then if you only make images at certain positions of energies of elements, you start seeing the distribution of the different elements. So now we can also study the distribution of the ejecta. And depending on these regions, you can also define the spectral extraction regions, and you can really study, for example, these regions where we find strong iron emission, and or also these jets which are seen in Cassiopeia, and you clearly see that there is a very different type of spectrum. So this now tells us also about the dynamics of the explosion, because using the spatial and the spectral information, we can also start understanding why this supernova remnant looks like this. And of course, the origin must be the explosion itself. So we can now start also comparing to supernova explosion models. And to get a very good understanding of the ejecta distribution, we can also look at other wavelengths, like this is now in infrared. You see the dust emission and also other line emission from similar elements like what we see in X-rays. And if you then combine, you can look at the position and the shifts of the lines at each of the position, you can start reconstructing the 3D structure in such an environment. This is what has been done here for Cassiopeia A, and this is also very important for our understanding of the dynamics of the explosion, but also for the nucleosynthesis that occurs in a supernova. All right, there are other interesting that we have been also finding using such X-ray observations of supernova remnants. For example, the fact that we typically assume that a plasma is, when the shocks run through a plasma, it's ionized and then it is slowly adjusting the properties. So it is usually under ionized and it continues to ionize until it reaches some equilibrium. But then in some cases also features in the spectrum was one which we call the radiative recombination. So there is also plasma that is recombining in the supernova remnant. And this is what you can see as the continuum here in this spectrum of, for example, IC443, that's a Sasaki spectrum. And what is shown here in the magenta, these are emission, the continuum coming from the radiative recombination. And this tells you that there is also parts in the plasma in the supernova remnant that is recombining. So it must have been over-ionized and then recombining now. And typically this is found in objects that are interacting with strongly with dense interstellar medium, where you have like evaporated clouds inside, and there is a lot of cooling going on. So another example is W49b in our galaxy. Similarly, you see a radiative recombination continuum, and this one is also known to interacting heavily with the dense interstellar medium. Yeah, and this is again a Chandra image, but it combined with infrared emission. So all this diffuse emission is coming from interaction with a dense medium around it. Another thing is charge exchange. Most likely you are all very familiar with X-ray charge exchange by now. This was something very new when we, like after Rosat, when people realize that there is also emission that is indicative of interaction of highly ionized species with neutral medium. So in supernova remnants, for example, this was observed in the Cygnus loop that you see here. So on the right-hand side, you see the radio emission. It's a very big supernova remnant also. It's an extended supernova remnant. It's an old supernova remnant UA, already in the radiative phase. And if you look at X-ray spectra, X-ray emission, you realize that there is some charge exchange emission in X-rays. So at the outer rim of Cygnus loop, you see that there is some charge exchange going on. Another thing that I wanted to also discuss is the element distribution we saw before. Another example here, and this is the brightest supernova remnant now in the Large Magellanic Cloud, N132D. On the right, you see this nice Chandra image with high resolution, where you see clearly interior structures coming from the ejector, but also some interaction with the outer medium. And already in the very beginning, when we started getting those images, we did some narrow band images again, and where you see clearly a difference in the distribution of the different elements. So a lot of oxygen is found in the interior, in the ejector. So this is also a remnant that is called an oxygen-rich supernova remnant. And we believe this comes from a very massive star, the explosion of a very massive star. And as most likely, you know, he told me this was the source that the supernova remnant that has been observed with Hitomi. Before it failed, unfortunately, and we couldn't get more information. And what you see here is the result of this Hitomi observation. So since there was a calorimeter, there is now a very high resolution spectrum. You see these data, so that's only around some emission lines. This is around iron, this is silicon. And so you can now even measure line width and line shifts. It's not like in the CCD spectra where everything is a broad Gaussian. And based on that, the Hitomi collaboration found that there is some redshift going on in the iron line, but not in the silicon line. So now you see, you can even measure in the spectra in X-rays the different distribution of and dynamics inside of supernova remnant if you have such a high resolution spectrum. And another interesting thing is if you look at this spectrum, it's not only the iron lines, the heavily ionized iron lines that you see, you also see some charge exchange line. And this was also observed already before, but as a hint, only like an additional bump next to the iron line in the Sasaki spectrum and, new star studies before, but back then this was not really resolved. But the fact that there is some charge exchange, so neutral iron line is showing us that there might be some cosmic ray acceleration also visible here, where cosmic rays are interacting with the ambient medium and excite this neutral iron emission. Okay, these are now supernova remnants that you can look at separately in detail, but you can also study an entire population of supernova remnants and learn about their evolution and about the properties. That's right what we do as astronomers, to look at a larger sample to try to understand some classes of objects. And the best place to do so is the Large Magellanic Cloud, since it's the largest and closest satellite galaxy of our Milky Way. And this is an image now taken with eROSITA. You see you see very nice diffuse emission, but this is not what I'm going to talk about. I could talk about that, but I'm not going to talk about today. But you see also all these nice points, especially those yellowish ones. These are supernova remnants. And before we had the data with eROSITA, we have been already studying those using some pointed observations with XM and Newton in a survey led by Frank Haber. And the results of this, many of you have already seen, I guess, is we have now sampled a lot of supernova remnants in the LMC, and now can also study, for example, the evolution of supernova remnants. Now this is a collection made by Pierre Magui only on type 1a supernova remnants sorted by their age. And as you see, so and you should also see that this is rather small, very small. This scale bar is always 1 arc minute, so this is a few arc minutes big here, and this is below 1 arc minute. So you see how the type 1a supernova remnants change over time. And the interesting thing is, at some point, what you see is a shell of shocked ISM in red. But then you see this greenish emission. This is mainly emission coming from the iron. So at the end, you see a lot of enriched material from the supernova or supernova remnant, and enriched by this iron that was produced. Another thing that you can do if you have such a large sample is to look at their morphologies, and this is now a collection of only core collapse supernova remnant. And you see core collapse supernova remnant has very different shapes and colors, which means also different types of spectrum. And this is mainly because these are remnants of massive stars which have changed their environment strongly during their lifetime, and depending on how the massive star evolved, you will also see different types of emission. And for example, the study of morphology has been also done also by other groups, especially also using Chandra data. And what you can, for example, do, what has been done is looking at the shape using some mathematical methods. So you calculate the multiple moments of the shape, and then you use some numbers like the quadrupole ratio or the octuple ratio to measure some properties of the shape, like the ellipticity and elongation or the mirror symmetry. And this is what is plotted here by the work by Laura Lopez. So the ellipticity and elongation over the asymmetry, and what you see is that there is a clear separation between the core collapse supernova remnant and the type 1a supernova remnant. And this is also what we've seen before. So core collapse supernova remnant have these very different shapes, morphologies, while type 1a seems to be more spherical. And another thing, what you can also look at is, for example, type specific lines, especially iron K line. If you have a hot supernova remnant, young supernova remnant, as I said before, this emission that you see strongly depends on the ionization. And ionization also means that it also changes the position of the transition line. So if you have a highly ionized iron, then the K alpha transition will be at a little bit at higher energies than if you have a not highly ionized iron. And this is shown on the left-hand side by publication of Hiroya Yamaguchi. You see how this position of the centroid changes. But also, if you take the ratio, you will also see some transition in the flux ratio. So this information can be also used to study the properties, the ionization of the plasma in supernova remnants. And what have been then found is typically that type 1a supernova remnants are found at lower energies. The K alpha line is found at lower energies. Then for core collapse supernova remnants, which you see in blue here, are found at higher energies, which means that they are higher ionized. So, and since this line ratio, this also depends on the density. This again shows you that the core collapse supernova remnant the progenitor of the core supernova remnant have changed their environment quite a lot through mass loss. And this is something that you can still see in the supernova remnants. So there's a lot you can do with supernova remnants. Study the supernova itself, you can study the plasma properties in general, you can study evolution of supernova remnants, you can study the interstellar medium. And this is what we want to do with Athena, because we will now have a telescope with much higher sensitivity and higher resolution. And here an example taking from Williams et al., where you see a comparison between the Sasaki spectrum and the Athena EXIFU, where you will then have these high resolution spectra. You can really resolve each of the lines. You don't have this, as I said, the bump-like Gaussian line features. This is a supernova remnant in a galaxy 397, rather young, and it nicely fits in the field of view of EXIFU. So you can study the plasma of each of these positions inside the plasma structure inside the supernova remnant very well. And that's something that will help us to understand not only the plasma itself, but also the evolution and the mixing and so on. Another thing that you might have also seen is if you look at the rims of and also smaller scale structures, since we have the spatial, we would have the spatial resolution plus the spectral resolution, we can also look at the dynamics in each of the position of supernova remnants. So this is a simulation of a Tycho supernova remnant again. So you should look at this blue line. That's the simulation for EXIFU compared to what we can get right now from XMM Newton EPIC PN. So the green is what we would see with EPIC. So with Athena, we would be able to really measure velocities in supernova remnants. Then, of course, you can get the 3D properties, the dynamics, and this will then again help us also to understand the explosion mechanism, which created such a supernova remnant. Then here is such as a comparison between the different instruments that we have or will have. So here below you have XMM Newton, Sasaki, Chandra, and so on. And the Chrism resolve is here in dark brown. So here soon, hopefully, we will have high resolution spectra also in the same energy range. But if you compare that now, what you can reach with achieve with Athena, it's more than 1 order of magnitude different for such a thermal plasma. So and also the comparison between Athena, WFI, and XMM EPIC is tremendous. So the sensitivity will help us a lot to the higher sensitivity to study this emission of the plasma in such objects. Then this is a nice simulation that has been done by Fabio at Zero, where if you have such an EXIFU observation, for example, of the Kepler supernova remnant, we can get this 3D information, which means that you have the spatial information, but then for each of the position you get the spectra. And what you see here is in these ring or I don't know, these layers are each of them are emission lines, so you can get the spectral information over the entire remnant, so you can map the elements, the metallicity. You will get a 3D reconstruction of the remnant and therefore also of the explosion mechanisms. And then a few words about extragalactic supernova remnants. We have been talking about large Magellanic Cloud. This was, and of course with XMM Newton and so on, we could also study maybe up to nearby galaxies like M31, maybe even to M83 something. So, but this would that was already the range in which you could study the population remnants, but not much in detail. You can measure the counts, maybe get the hardness ratios, but that was it. And now with Athena WFI, we would be able to perform such similar studies which we were doing for M31, M51, M33, even to much higher distances. So here you see M51, a nice Whirlpool galaxy, nice interacting galaxy. This was a Chandra observation for which we almost needed 1 million seconds. And you start seeing the diffuse emission, you start seeing the difference between the merger, so the satellite galaxy and the main galaxy, and all these points, these especially the yellow ones are supernova remnants, and M51 is also known to have supernovae. It's has an unusual amount of occurrence of supernovae. And if you look at it with Athena WFI, so this is a little confusing. I have to explain it. This is only a simulation of the diffuse emission. And then I just added point sources at different positions with a typical luminosity that you can expect from a supernova or supernova remnant, brighter supernova remnant, just to be able, and I wanted to see where you can resolve it, really detect it, significantly detect it. And you can really go down at the distance of M51, you can definitely go into the nuclear region and detect them. And even if you go at 10 times of the distance, you will be able to detect such bright emission in the outer parts of such a galaxy. So in total, you will be able to study supernova remnant, which we know can be as faint as 10 to the 34 ergs per second, so up to a distance of 2 megaparsec. But for the typically brighter ones, 10 to the 36, 37, up to 8. We can go out into 60 megaparsec, and supernovae, when they occur, they can be even higher, even brighter, 10 to the 39 or so. Then we can detect them up to 200 megaparsecs. And this is only possible with that sensitivity that we have with Athena. And with that sensitivity, and then combined higher spectral resolution, if you use XI2 for the closer ones, like in this case, it's a simulation for 3 supernova remnant at 3 megaparsec. You can even, based on the spectra, you even distinguish between the types of the supernova. So, and also study the history, like did the massive star have a strong stellar wind or a rather weak stellar wind? You will see the difference in the X-ray spectrum. So there is a lot that we can do. We will be able to do with WFI and XIFU if we have Athena. And that's already, the end of my talk. Just give you a summary. So if we study supernova remnants, of course, they are beautiful, but there is a lot of good physics that you can do. You can study supernova explosion, nucleosynthesis, even study properties and the history of dust. Shock waves in general are very interesting. Hot plasma is interesting. And then, of course, what is very important for the study of galaxies in general is the interaction of the shock waves with the surrounding medium, and also the particle acceleration that occurs in galaxies. And with Athena, we will be able to do spatial resource spectroscopy with very high spectral resolution, which will allow us to do some spectroscopic diagnostics of the emitting source. We can measure velocities, both bulk and turbulent velocities in those remnants. We can determine progenitor type, the supernova explosion time, and also the type and the mechanism. And we can even study extragalactic supernova remnants up to quite a high distance. And that's what we are looking forward to. Thank you for your attention.
Thank you very much, Manami. We are now open for questions. And again, you can either put questions into the Q&A or you can raise your hand. And as people are beginning to think of their questions, I'll just note that we are going to take a break for the rest of August on this webinar, and we will restart later in September. The list of new talks will be coming out in early September, so keep a lookout for that. And we have our first question. Let's see. Sorry, I can't quite see the name now because of the way this works. So Sarah, please, you should be able to unmute and talk.
Yeah. Okay. Thank you, Professor. That was a really nice talk. I was just wondering why is there a high supernova rate in M51? Like, is it a star-forming galaxy, or is there other reasons why we observe more supernovas?
Yeah. That's a good question. M51 is a strong, highly star-forming galaxy. So yes, that's the reason. And I think this interaction, this merger also changes the property of the ISM. So it also enhances the star formation. So this is right now it is in a period in which there are much star formation going on, and therefore most likely also supernova occurring.
Okay, thank you. And my other question was, how do we realize when the remnant is in equilibrium? Like, during what phase of the evolution do we say that the supernova remnant is in equilibrium?
Typically, the supernova remnant, so the plasma in the supernova remnant will reach equilibrium when it is older, so it has time to relax. But as you have seen, there can then also be cases in which there is some mixing of material from the surroundings. Then it will again disturb the properties. So yes, but usually young supernova remnants are rather not in equilibrium.
All right, thank you.
Thank you. Matteo, please.
Yeah, thank you. Thank you, Manami. Very interesting talk. Interesting also for the Athena perspective. And my question is implicitly related to that. From existing Chandra results, so Chandra spatially resolved spectroscopy, can we tell if there is a typical spatial scale over which the dynamic of the plasma changes significantly? Because this, of course, could create troubles with an instrument with a poorer spatial resolution than Chandra, when we wanted to make real dynamics of the plasma and create maybe 3D maps of the plasma dynamics in the remnant.
I understand. Yes. Yes, such studies has been already going on quite a lot. And of course, I cannot tell you numbers, so I cannot say it's on few parsec scale or something like that. But if you look at images of Tycho, for example, you see this small scale. I can't go backwards in the slide. Sorry. So you have these clumps and you have these filaments that are created. So these are the typical scales you can observe and study, and yeah, so it depends on what objects you look. For example, for Tycho, or yeah, in principle, yes. Also the nearby remnants. I think the few arc-second resolution that we expect are good enough to study such differences, because now we have the sensitivity, so we can have more photons already in a short time, so we can get a high quality data in this small region already. And while with Chandra, you needed to observe quite a long time to get high enough statistics to do such a study. So definitely, it will be an improvement.
Okay. And if I may, Randall, just a curiosity on slide number 9, I think you showed an image of Tycho, if I remember correctly, where you saw these stripes. And I had the impression that there were also like loop structure, similar to the kind of structure we see in the sun corona. Is just an optical impression, or this kind of loop have been seen?
Yeah, I think I know what you mean. Let me just see if I can run this again, start this again. I don't know why it doesn't work. I'm sorry, taking these. So you mean this thing, right?
Yes, and also more in the center, of course, eyes is very efficient in creating structure and recognizing patterns. But
so those things I would say are projection effect, and it's coming from mainly coming from the mixing from the contact discontinuity, where you have the shocked interstellar medium and shocked ejecta, and you have turbulent mixing. So if you would look from the side, then you would see something like corresponding to these stripes from the relativistic instabilities or other magnetic field instabilities. But this, if you look on top, you will see these, diffuse emission structures that come from that mixing. And this is actually very consistent with also what hydrodynamics and MHD simulations show, like what people do, Marco Micheli or Salvatore Orlando do in Palermo.
Okay, thank you.
Okay.
Thank you.
And then we have a question from Nanda, and then I think our last question from Maximilian. And so
thank you very much, Manami, for the very nice talk. I have a couple of questions, maybe related, maybe not. So the first one is there anything which can give us somehow unambiguously or with a small error or not very model dependent, an idea on how much mass went in the reverse shock while looking at the core collapse remnants, for example?
How much mass went into, I mean, the reverse shock goes into the ejecta. So this would be the ejected material.
So, so my question, it goes more trying to understand why some of the compact objects that we see in the center of remnant, some of them are expected because of their current magnetic history, their current observational property at the moment, are expected to having had a lot of super Eddington accretion at the beginning, right? So my question is there anything from the remnant that we see that can give us a trace on whether this was really effective in some of the remnant and was not in others?
So you can to a certain extent, but there are uncertainties, try to constrain the mass by looking at the emission. But of course, in that case, you need to have a system in which the reverse shock already went through the entire remnant. And for example, for Cas A or Tycho, most likely also is still not the case. So you don't see on the entire ejecta in X-rays. But as you have also seen in, for example, Cas A is very bright in infrared. So you can also use the infrared emission to constrain the amount of cold material inside the supernova remnant. I think if you combine all that information, you can get some constraint on the mass. How significant that is, or how accurate it is, and if you can really make any statement about the accretion on the compact object, I don't know. I guess that's something one could try to estimate on known remnants or remnants in which some ejecta emission already has been analyzed in such a way.
Okay, thank you very much. I have another question, but maybe there is no time for it. Is there Randall?
No, I think we should move to.
Okay, yeah. Thanks.
Thank you.
Hi, thanks for the nice talk. I have a question about Cas A. You showed the nice jets. and
Yeah.
it looked like there was a counterjet. Do they come from the compact object because there is some residual accretion? And it almost seemed to me like there were 4 jets on the side of the counterjet. There were some more jetty looking things.
Where was that? You mean this? No, so this is one jet-like structure, and then there's a counter jet. I think what you mean is like many jets. This is like part of one jet, and these jets are most likely created were already created in the explosion. So some asymmetries that you had in the explosion. There are theoretical simulations that try to reproduce that. But I don't believe that is something that have been created afterwards by the compact object, because the compact object in case A is a CCO and it's very quiet.
Thanks.
Okay. Well, we are past the hour. So I know Nanda still had another question, but perhaps you can take that offline. So I'd like to thank again Manami for such a wonderful talk, and remind everyone that we will restart in September. So watch your email inboxes for the next talks. So thank you again, Manami.
Thank you.
Thank you very much. Thanks.